Hello, everyone. Thanks for joining us today. My name is Omar Faruqi, and I'm the Business Development Manager at Northern Crescent. I welcome you all. But before we start, I want to go over a few housekeeping items. Firstly, there is a question and answer session box on the left side of the window. You can ask questions anytime during the presentation. This window is moderated, and there may be a delay in seeing your questions in the main window. I also recommend you to please drop your name with the question, but you can also choose to be anonymous. Secondly, the recording of the webinar will be available to all participants, and we will send a link via email by early next week. And lastly, our apologies in advance if we face any technical challenges, although we have taken necessary precautions in this regard. So season's greetings to everyone. Hope you are all getting ready for the much anticipated summers. But this change brings caution to all of us. Throughout spring and summer, the number of motorcyclists on the road will increase. So it is important for both car drivers and motorcyclists to be aware of one another. Motorbikes are known to create additional blind spots for car drivers, and several accidents occur due to these blind spots. So I want to take this opportunity to remind us of the key safety tips as advised by various regulators and safety experts. So number one, for drivers, they must allow greater following distance behind a motorcycle. They should also show extra caution in intersections, as most crashes occur when the drivers fail to see a motorcyclist and turns in front of them. And importantly, drivers should never try to share a lane with a motorcycle. At the same time, motorcyclists should avoid riding in poor weather conditions. They should position their motorcycles to avoid drivers' blind spots, and motorcyclists must use signals for every turn or lane change. With this, enjoy the summers and stay safe. Now, before we dive into today's topic, I request you all to please take a moment for this short poll. Realizing the diverse participation today, we thought it may be interesting to share groups' experience distribution with you all. We'll share the results of the poll towards the end of the presentation. So please follow the link below that you can see on the slide. And probably we are going to drop it in the chat window as well. So please follow the link and pick one option. I'll wait for a minute for all of us to complete this question. The question reads, in your experience, what is the most common source of cost overruns on pipeline projects? Number one, inadequate definition of project scope. Number two, route changes due to stakeholders and landowners' concerns. Number three, inadequate details of pipeline design in drawing packages or construction work packages. And number four, field changes during construction. Please take your time to fill up the poll. And choose one option, please. So the link is posted in the chat box. You can access it from there. All right, let's proceed with the agenda. So for today's agenda, before I hand over to Dr. Roy, I will take a few minutes to talk about Northern Crescent, what we do and how we add value to our clients. Thereafter, Dr. Roy will dive deeper into the pipeline design and integrity considerations with focus on pipe-soil interaction and what opportunities there might be for improved design and cost efficiency. We'll be referencing P-Terrain as one of the tools through the presentation. So who are we and what do we do? Founded in 2010, we are a team of specialty engineers and our portfolio spans across a wide range of industries, pipelines, and facilities applications. By discipline, we are segmented into pipeline engineering, facilities engineering, integrity and fitness for service, industrial HVAC solutions, and regulatory and compliance services. And by pipeline capabilities, we deliver detailed design, geotechnical engineering, stress analysis, and terrain mapping solutions for a variety of applications and pipeline sizes. Today, our experience maps onto 3 continents. With the majority of our work in Canada, we have also serviced our clients in the US, Latin America, China, South Korea, and parts of the Middle East. We operate with 2 offices, having our head office in Calgary and branch office in Grand Prairie. And it's not all about the volume of work we have delivered. It's all about the quality as well. Our QHSE track record has been flawless. We never had a design failure or any employee incident in our office or field locations, and we are really proud to highlight that. And in the end, an important note to highlight, as a company, we want to differentiate and progress ourselves by being part of the new trends. Despite the external industry pressures over the last few years now, we kept our focus on R&D and continuous improvement. And I'm proud to highlight that we have registered over 350K spent on R&D projects during the last 2 years alone. Now, for an engineering firm of our size, this is a significant commitment. Yeah, here is a quick snapshot of our GP office. We are located on the main avenue to the downtown area. So if you are in Grand Prairie, it's hard to miss. This office is operational since March this year, and we have made this commitment to support our clients better by being closer to the action. This office is led by a senior process and project manager, and it offers us additional ability to eliminate time for site visits and surveys. Now, in today's competitive engineering world, Northern Crescent stands out by staying focused on 3 pillars of differentiation: diversity, innovation, and automation. With our team of hand-picked professionals, we incubate diversity. Having the good balance of experience across our teams helps us harvest innovation and drive efficiency and continuous improvement for our clients. Our team of professionals also comprises of software engineers that are helping us to develop innovative tools to drive performance efficiency and cost optimization. Today, we have more than 8 in-house tools and over 60 in-house specifications. Now, without going into much detail, here is a high level of some of the in-house tools that you may find interesting from pipeline engineering perspective. P-Refine on the top left side is a robust tool for refining the ILI data that precisely provides existing bend locations, bend angles, bend radii, offering additional analysis to our clients at no incremental cost or time. P-Stress is a fully automated pipeline stress analysis tool with visualization interface. P-Route generates high-quality pipeline alignment sheets by integrating large and complex databases, literally with a few clicks. P-Build is also a fully automated tool for pipeline lowering stress analysis. and HDD pullback stress analysis that saves valuable time at construction sites and drive quality. PBOR is a fully automated HDD design tool that helps design HDD profile for a variety of crossings. And PTerrain is again a fully automated geotechnical terrain mapping tool that utilizes GIS and helps identify soil types along the pipeline path. We would be referencing this in today's presentation. Now, without further delay, let me hand over to Dr. Shama Roy to take us deeper into the topic. Dr. Roy holds a PhD in pipeline geotechnical engineering and specializes in pipe-soil interaction. He leads the Special Projects and Pipeline Integrity Group at Northern Crescent, and he is actively involved in large-scale projects and latest research with various Canadian universities to better understand the practical implications of pipe-soil interaction. Dr. Shama also contributes by participating in industry forums and code committees. Please refer to our website for his latest publications, and you are welcome to reach out anytime. Without further ado, Shama, the floor is yours.
Thank you, Amar, for the introduction, and thank you everyone for joining in today. Excuse me. So before I jump into the technical aspects of the main presentation, I want to acknowledge my colleague, our GIS specialist, Gananda Gurung, and our pipeline stress specialist, Anand Murshid, who helped me building the slides. I have approximately 25 slides, so bear with me for the next 30 minutes or so. Again, this is not a technical presentation, so what we'll try to do is we'll try to use the technical example to give you a high-level overview on how the terrain map that we developed in-house can help your pipeline design. Just as a refresher, I thought we should discuss about the pipeline design in 2021. Just in lack of better wording, I have divided it into two approaches. Number one is the mechanical design approach, and number two is the 360-degree design approach. So the mechanical design approach is a simplified approach, mostly considered in the mechanics of the pipeline and with the assumed data for soil. On the other hand, your 360-degree design approach is more like a comprehensive approach, and it considers mechanics for both soil and pipeline. And we use generally relevant soil data for your 360-degree design approach. Now a little bit more into the mechanical design approach. I know it's like a bit busy slide, so the key takeaways from here is in your CSSG 662, it has requirements for your minimum soil cover, for example, your clause 4.11, but no detailed methodology for criteria on evaluating your pipe soil interactions in different soils. In other words, their stress analysis is performed based on the assumed soil properties, which results in a more subjective analysis. And regardless of the soil along your whole pipeline right-of-way, generally we define or specify the bands with 20D and 40D band barriers. Again, this approach is typical for short pipelines. Now, some pros and cons. Some pros, these approach can be adequate for pipelines that are operating your less than 30% of your maximum operating pressure and your temperature difference for 10 to 15 degrees Celsius. And obviously, it's definitely a low cost solution. Some of the cons, definitely it has some unknown risk if the pipeline are operating at generally greater than 75% maximum operating pressure and you're greater than 80% of your design temperature. Now, on the other hand, your 360-degree design approach is basically, in this approach, a desktop study is first done for your entire pipeline right-of-way to determine the soil classifications, which is also known as terrain mapping. And generally, this is done by a geotechnical vendor. And based on the terrain mapping, additional geotechnical testing might be carried out depending on project to project and depending on the conditions of your specific projects. And therefore, after following this terrain mapping and the soil properties that you're assuming from this terrain mapping, a detailed stress analysis is carried out with relevant soil properties for your actual right-of-way. Now, again, this approach is typical for the large transmission pipelines. Now, some pros, the pipeline has high reliability regardless of your design conditions and soil conditions along the whole pipeline right-of-way. Some cons is definitely high costs of field program longer design schedule, and definitely an increase in cost and schedule due to involvement of two separate vendors. For example, if you're doing the terrain mapping by a geotechnical vendor, you're doing and you are doing the stress analysis by a stress vendor. Now, not only the pipeline design itself. So if you are designing your buried pipeline, in most of the cases, you need to deal with soil. So for example, your thermal expansion behavior, in other words, the thermal stress analysis, which is more primarily related to your pipeline design. Other than that, your global buckling, whether it's a lateral or upheaval buckling, your ratcheting issues, your geohazards, either it's like a rapid landslide or a slow ground movement, and your hydrotechnical hazards, or you name it. So in most of the cases, you need to deal with the soil, and the behavior of your pipeline can vary based on the difference in the soil types. Now it leads to a question. So can pipeline fail due to thermal expansion? Again, this is a classic example of pipeline rupture that occurred on 17th October 2013 near Fort McMurray, Alberta. And the Transportation Safety Board, the whole investigation report is available there. So they mentioned the reason as during normal pipeline operations, thermal expansion has developed in the pipeline that exerted force on the elbow, resulting in increased stress in the interdose on elbows. Over a 50-day period prior to the rupture, the pipeline had been operating at a sustained temperature ranging from 42 degrees Celsius to 48 degrees Celsius and a maximum pressure of the range of 9,000 kPa. Now, the interesting thing is the soil condition at the rupture site consisted of an organic deposit, which is popularly called as muskeg, approximately 0.5 meter to 1.5 meter thick with underlying clay. Now, with all this being said, the focus of our today's presentation would be how the mechanical design approach that we discussed of the pipeline can be improved. And we will definitely refer our own in-house tool, PTrain, that we have developed in-house. A little bit background of how we take soil into account your pipeline analysis. Generally, your soil around your pipeline is represented by three orthogonal soil springs, as you can see on this slide, naming lateral, axial, and your vertical springs. Just to note that vertical springs has two different stiffness in upward direction and bearing direction. So basically, in other way, you can say there are four soil springs. One is lateral, one is axial, one is uplift, another is bearing. And the available guideline to model the soil springs or define the soil stiffness are popularly American Lifeline Alliance 2005, Pipeline Research Council Institute 2009 and 2017. Now, to define the soil spring, what you basically need is the peak resistance of your soil and the displacement to reach that peak force. So if you know these two information, you can actually define the soil spring along your whole pipeline. Now, just to give you an example, this is a sample calculations for PRCA 2017. Now, I know it's a very busy slide, but what's the takeaway here is by using sort of 8 or to 10 equations, you are actually able to define your whole soil springs, all the four soil springs. Now, the major thing from here is like, what are the soil parameters that we need to define these soil springs? The major soil parameters that we basically need is undrained shear strength, your friction angle, your unit weight of the soil, your soil cover or burial depth, and coefficient of earth pressure at rest. Now, even if we further refine it, basically the two strength parameters that we need to define or to do the pipeline analysis is the undrained shear strength, which is basically for clay type soil, and your friction angle, which is basically your sandy type of soil. Now, if we know these two important information, we somehow will be able to define the soil springs along your pipeline, and we'll be able to define the complete pipeline analysis. Now, instead of just being said that, okay, our terrain mapping is actually helping improving the pipeline design, why not we see an example? So this is a practical example that we'll be showing all over the presentation. So this is a sample pipeline, as you can see. It's a small pipeline, NPS 10 with design temperature 55 degrees Celsius, installation temperature -10 degrees Celsius. Your specified minimum yield strength is 359. We assume the soil cover 1.5 meter, wall thickness 6.4 millimeter, and your maximum operating pressure is 9.93 MPa. And this pipeline has total 34 bends, as you can see on the right-hand side. And the bends vary from shallow angle from 7 degree to like maximum 90 degrees. So it has like a wide diversity of your bend angle. And just to make it simplified, we have defined all bends with 20D bend radius. Now, the main target of this example is not to do a whole pipeline design, rather to show how this terrain mapping can help to improve your design. So the main things that we are going to change here is the soil parameter. So we are keeping all the bends as 20D, all the bend information, and all the pipeline properties, as you can see in this screen. Now, for this pipeline, now we need to do a thermal stress analysis. And generally, we don't have a luxury for a smaller pipeline to have a detailed geotechnical report or any soil information. So we need to assume something. Now, you probably give the same pipeline to two vendors, and case one is probably the one vendor is assuming a soft clay with 15 kPa rain shear strength, which is very reasonable and it's a common practice. And probably other vendors say, no, we want to be more conservative and we want to assume loose sand with 25-degree friction angle. So you can have two cases for the same pipeline, and both are reasonable assumptions, I would say. Now, what we did here, we actually ran the same pipeline. We ran this pipeline stress analysis with both cases. So first one is soft clay with 15 kPa rain shear strength. As you can see here, these are the your spring properties or your spring stiffness for 15 kPa soil, soft clay, and these are the your spring stiffness for your loose sand with 25-degree friction angle. Now we ran the analysis, and we can see for your case one, which is soft clay with 15 kPa rain shear strength, your number of failed bends are 30. So by failed bends, I mean where the stress has actually exceeded your SMOIS or your specified minimum yield strength. So for your case one, your soft clay with 15 kPa rain shear strength, your number of failed bends is 30. Now, if I look at the case two, with a loose sand with 25-degree friction angle, now your number of failed bends are 25. And generally it is expected because when you are assuming a loose sand, you are assuming a lower strength compared to your clay type of soil. So in summary, we have done these two cases. Pipeline stress analysis, simple. We haven't changed anything else, just changed the soil properties. And for for case one with soft clay, we found like 13 bends failed, which is further measurement or further action. In either like a solution with increasing bend radius or whatever it is. For your case two, loose sand with friction angle, your total number of failed bends are 25. So there is a gap between these two. Now, let's see how this terrain mapping can actually help this analysis. So before we jump into that one, what is basically a terrain mapping? So terrain mapping provides information about landforms and the distribution of your surfacial materials, natural processes operating at the landscapes. In summary, what the terrain mapping can give you is the soil properties along your pipeline right of way. So in other way, the pipeline that is crossing the soil types, different soil types, terrain mapping can give you information on those soil types. And generally terrain mapping is done based on a desktop study. So by leveraging the publicly available datasets on soil information. Now, what pTrain can do. So we have developed our own in-house tool, our software, which we named it as pTrain, so which is basically pipeline train. So pTrain is an in-house tool or software for terrain mapping. It has a robust data set for soil for several provinces, for example, including Alberta, British Columbia, and Saskatchewan. Right now, we are trying to include other provinces and obviously some other states in US as well. A unique solution of the pTrain is it has a significant, enormous, large data set of wetlands in Alberta, which we popularly know as muskeges. A supporting data set of publicly available geotechnical boreholes and reports. So why we have added this publicly available geotechnical boreholes and report, just to give you a second level of safety for your educated guess of the soil parameters by the geotechnical engineers. So it's not only that geotechnical engineer or in-house geotechnical engineer actually get the soil information from the terrain mapping, they can also compare if there is any available geotechnical borehole or reports closer by that area. So they can give a second level of safety on understanding that. And finally, the pTrain actually provides information about the soil profile, geological information, your wetland or muskeg information, and the topography of the selected region or center line. So in general, if you have the pTrain and you run your pipeline right away through the pTrain, it can actually give you a lot of useful information, especially on the soil types, what type of soils the pipeline is crossing. Now, I know it's like a little bit hard to visualize by just simply listening, so why not we see what ptrain can actually give you. So ptrain actually gives you a map like this. As you can see here, your pipeline is crossing different types of soil, as you see by different polygons and colored polygons. Now I see these like letters a little bit small to read, but if I zoom it out, excuse me. So what it gives, like it gives you the chains to and from and the different types of soil name, so A, B, C, D, E, and the texture class, for example, whether it's a silty clay or clay, and it also gives you a surfacial geology. Now, not only that, if you zoom in, for example, this section here, type E soil, what it can actually gives you a soil depth. So for example, from 0 to 13 centimeter, 13 to 20 centimeter, what type of soil you are assuming, or what type of soil are there. And not only that, it will also give you a percentage of sand, silt, and clay, right? So let's say, for example, your depth of cover is 1.2 meter. In that case, you can have an idea that you have a clay loam type of soil, and you're expecting around 24% of sand, 38% of silt, and 38% of clay. So now, instead of just making a wild guess, you have more information to gauge your soil properties or to assume your soil properties. Now, as we did, as I showed, like we did two analyses. The case one was soft clay with 15 kPa rain shear strength. Case two was loose sand with 25-degree friction angle. Now we are adding case three, where we are using this information for terrain mapping that I just showed you, and we are not counting any muskeg right now. So terrain mapping without the muskeg. So what I can get from here, from the terrain mapping, I can get the soil, different soil identifier that your pipeline is crossing. I know what's the percentage of sand, silt, and clay, and then I can have a better, I can assume a better soil properties based on this information that you have. So for example, let's say type B, we have only 7% of sand and rest 93% is basically clay type soil. So it's like reasonable to assume a higher rain shear strength for clay for this type of soil. On the other hand, if you see like type E, we have 24% of sand and 76% of clay. So as we have a little bit higher percentage of sand, we are assuming a lower rain shear strength, for example, 30 kPa, right? And then we do the analysis. Before we do the analysis, we actually define the soil properties using the same methodology for defining the different stiffness for all this type of soil. We included it in the model and we run the analysis. So what we're seeing here again, the case one, your soft clay with unrated shear strength, number of failed bends were 13. Your case two, loose sand with 25-degree friction angle, your number of failed bends were 25. Now, as we're using the terrain mapping without the muskeg, our number of failed bends are now number 9. So this is definitely an improvement. And I mean, we are not doing any wild guess. Now we have a more educated guess for your assumption of the soil parameters. So you can see that it can actually significantly improve your pipeline behavior as well. Now, another interesting and the unique thing for ptrain is the addition of the muskeg and the wetland database. As I mentioned, we have included an enormous data set of wetland or muskeg, primarily for Alberta in our data sets, and we have changed some attributes to make it clear. As you can see in this picture, our pipeline that we use for the example was somewhere like here, but you can see it can actually give you a lot of information on the muskegs and the wetlands. So basically, if we see here, the same pipeline that we used, it actually covers a small region, or the pipeline crosses a region where there's a muskeg. So for example, if we zoom in out, you can see that your pipeline actually crosses the type D soil, which is defined as organic soil. So your organic soil is, in other words, is like a muskeg type of soil. Now we further zoom in, we can see, like we can actually see different types of muskeg. For example, bog, whether it's a bog type or a fen type or a marsh type or open water or swamp type. So it can give you a reasonable information about the muskeg as well. And we can see that this section of the pipeline is actually crossing a muskeg. So what we did here, so we actually did the 3 cases, as you can remember. The first one was soft clay with 15 kPa and rain shear strength. Second one was loose sand with 25-degree friction angle. And third one was we used our terrain mapping or ptrain and without the muskeg. So why not we add another case? So for example, the case 4 is basically using the same terrain mapping, but we are including the information of the muskeg or the wetland as well. Now, as you can see here, it's basically this A type A, B, C, E, F are same, exactly what we use for case 3. We are just adding the properties for muskeg, and we have defined as muskeg is a very weak soil. We don't want to take any weak, so we just defined as a 3 kPa undrained shear strength for now, for this example. Again, the same thing, we have defined the soil spring stiffness for different type of soil, from soil type A to soil type F. It's all same. We are just adding the soil type D, which is basically your muskeg, and we are defining the properties for your muskeg as well. Now we ran the same analysis, and just to give you a refresher, for our case 1, soft clay with undrained shear strength, it was 15 kPa, and our total number of failed bends were 13. For case 2, it was loose sand with 25-degree friction angle. Your total number of failed bends were 25. And for case 3, where we didn't use the muskeg properties, but we use our terrain mapping, we found the total number of failed bends on 9. Excuse me. Now with case 4, when you use the same terrain mapping by P-Terrain with muskeg, our number of failed bends are still 9. Now you can tell, yeah, there's not a significant improvement by using muskeg properties. But let's see a little bit deeper on it. So for example, when we had case 3, terrain mapping without including any muskeg, the failed bend was here. So this bend was actually failing. But when you use that muskeg with the terrain mapping information, instead of this bend, another bend is failing. So if you don't take these muskeg properties in your pipeline analysis, maybe you are like missing these pipeline bends that needed further action. So in summary, we have used 4 types of soil, or 4 types of analysis. Case 1, your soft clay with undrained shear strength 15 kPa. We saw number of total bends fail 13. We used case 2, loose sand with friction angle 25 degree, number of bends fail 25. We didn't use any sort of terrain mapping in the first 2 cases. It was just an assumption, and same assumption of soil for the whole pipeline. Case 3, we used our terrain mapping with a more educated assumption of the soil properties. We didn't use the muskeg. We found the number of failed bends were 9. And case 4, we used the terrain map and we included the muskeg, and we saw the number of failed bends are 9, but the bends that actually failed with the muskeg is different than the bends failed without the muskeg. So it needs to be considered. In summary, so integrating your desktop terrain mapping, otherwise P-Terrain, with mechanical design approach of the pipelines can significantly improve your pipeline design. So rather than making a wild guess of the one type of soil along the whole pipeline, you're making a more educated assumption, and your P-Terrain is actually helping you make that assumption and do a better analysis. Now, the P-Terrain can be used for different cases. For example, both for new pipelines and your existing pipelines. So for example, for the design of your new pipelines, definitely we have showed an example for thermal stress analysis. It definitely can help in the thermal stress analysis. It can definitely help you identifying wetland and muskeg locations in the area that you're planning to build your pipeline or facilities. And it can also help in your buoyancy control specifications as it is giving you more detailed information of wetland and muskeg. And similarly for existing pipelines, for integrity assessment, if you have an existing pipeline, you need a service change. For example, you are increasing your temperature, then you need to run the pipeline stress analysis again. Then definitely P-Terrain can help you to conduct that integrity thermal stress analysis. And you're definitely, if you have some section of the pipeline or segments that need replacement and you need the soil information at that place or at that location, then P-Terrain definitely can be helpful. One other interesting thing that happened, like Omar yesterday asked me when we almost finished preparing the presentation, like Shama, how many projects you have used, in how many projects you have used P-Terrain? So I initially thought it should not be long, but we actually used over 60. We actually used P-Terrain over 60 plus projects with 6 plus clients. And as you can see here, it can be as simple as a small feeder line to a long, like medium to large pipeline that crosses a different types of soil. So it doesn't matter whether it's a small pipeline or like a mid-sized to large pipeline, we can cover it all. And P-Terrain can actually give you a useful information of the soils. Now, the major key takeaways from here is basically the first terrain mapping using P-Terrain definitely provides a safer design for the buried pipelines. as we showed by the example. P-Train reduces the uncertainties in design due to soil assumptions, which I think is a very important step, because when you are making wild guess for your soil over the whole pipeline, you are actually going into a lot of uncertainties. So P-Train actually reduces that uncertainties in the design, which is coming due to the mainly due to the soil assumptions. And one unique thing, as I said, like the integration of this wetland or peatland, which is popularly known as muskeg areas, this really enhances the accuracy of the pipeline design by identifying that areas requiring spatial measures. So especially, I think all of you probably are more aware than me that where we have the muskeg sections, we need more spatial measures. And before you have any detailed information, this P-Train actually gives you a lot of good information, like where you're expecting your muskegs along your pipeline right of way. And definitely P-Train can generate a terrain map with the associated engineering properties of the soil for your pipeline design. And basically we can do it with, for small or short pipelines, we can do it within 1 day. And thereby we are ensuring a cost-effective solution for sure. So that's why we wanted to make it as a tool or software base that can actually run without a lot of involvement by the user itself. So the complete process is reviewed by a geotechnical specialist, because like when you're getting a percentage of sand, clay, and seal, and a lot of geological information, you will still need it to be reviewed by a geotechnical specialist to ensure the data accuracy and the relevance to your pipeline project. So we definitely do that as a second step after we get the map from the P-Train. And definitely P-Train ensures the improved cost and schedule for pipeline projects, even if it's like a larger projects, by providing a one-stop solution. So right now you don't need to go to 2 different vendors. One is geotechnical and one is stress vendors. Rather than you can come to us and it provides a one-stop solution. So we can actually do that terrain mapping by P-Train and also conducting the stress analysis at the same time. So that's pretty much all I had for today. We actually got the poll results in, and thanks for participating in the poll. So the question was, in your experience, what is the most common source of cost overruns on pipeline projects? And the results are pretty interesting. So we can see inadequate definition of project scope, which we also faced in many of our projects. We can see inadequate details of the pipeline is probably 3rd position, and field change during consideration is 3rd. In the second position as well. So in other ways, like inadequate definition of project scope is definitely, I mean, this is common, and we have faced that as well. Now with that, I will pass it to Omar. Thank you.
Thank you so much. It was insightful. Thanks a lot. Yeah, so just a note for everyone, I got a couple of messages that there are some challenges with regard to posting questions on Q&A. I have also dropped my email in the chat window. If you want to ask a question, please feel free to send me an email and I will include it in the Q&A right away. We received a question here, Shama, from Amit Azad, and the question is, I understand terrain mapping is giving a native soil data, but in pipeline backfill is a distributed soil data. So for your stress analysis, I guess you provided distributed soil input. How you get your soil parameters for distributed soil? Number 1. Number 2, I'm trying to understand your rationale for case 1 and case 2. Is your assumption relevant to the route, or it's just arbitrary conservative assumption?
Awesome. I think those are great questions, Amit. So the first question is like, definitely you are right. When we are doing the backfilling, so your native soil properties are not active anymore. But just instead of, you don't have any information for your backfill soil. So when you have the information on your native soil properties, you can make a more educated guess. So for example, your native soil has 20% sand and 80% clay. So when you're using that backfill soil properties, and if you're using that native soil as your backfill properties, now you can probably assume probably 50% of the strength of your native soil, or like 40 to 60% strength of your native soil properties. But what is actually giving you, or what the terrain mapping is actually telling you, is a more educated guess. So you don't need to assume, okay, it's just a 5 kPa or like a 10 kPa of clay, rather than you now know that in your native soil, and that area, you have different percentages of the sand, silt, and clay, and now you can make a more educated guess for your backfill soil. So in this way, your terrain mapping can be really helpful. And just to answer your question number 2, I think, yeah, for case 1 and case 2. So I mean, like for smaller feeder lines or smaller pipelines, I think that's probably pretty much the industry practice as well. So some people have used 20 kPa undrained shear strength in case they don't have any information, but 15 to 25 kPa of undrained shear strength for clay for your whole pipeline is, I mean, this is a reasonable assumption, and people are using it just to become more conservative. But now the question is, I can always tell, like, no, I don't want to use clay because you might expect a lot of sand along your pipeline, and for this smaller pipeline. So in that case, I can come up and say, okay, why not use loose sand and use 25-degree friction angle? So we are making a more conservative assumption. In other way, so what I'm saying here, like, it doesn't matter whether you see your 15 kPa to 25 kPa, or you assume your 20-degree to 30-degree friction angle, you are making a wild guess along your whole pipeline, right? And even if you use a 5 kPa or 1 kPa, you can never be like the most conservative solution. So sometimes it can give you an over-conservative solution, and sometimes it can give you a non-conservative solution, because your pipeline is crossing wide variety of soil, not just a simple one type of soil.
Okay, thanks, Shama. Shama, another related question here. Can you please explain again where pTerrain get the data to generate the terrain map?
Yeah, awesome. That's a great question. So right now we're using all the publicly available data. So for example, we have three steps. The first one is all the information that we're getting from Agricultural Canada or other federal bureaus. They have a lot of information on the soil data along the whole, let's say, for example, along the whole Alberta province. But that's the first step. So they have digital data set for those one. And the second thing is they don't have the digital data set for the whole province. Sometimes you have other information. Those are more like done a long time ago, and these are like hand maps that actually gives you this type of details. So we need to digitize those hand maps, and we have included the digitized data from the hand maps into our data sets. This is the step 2. And step 3 is we have also included that wetland or muskeg data set that is also we have taken from Government of Alberta. It's a huge and enormous data set. So our first 2 or 3 tries, like our computer actually failed or crashed because it's a huge data set. So we have included that 3. And the number 4, as I mentioned, we have also included the available soil reports. Those are publicly available geotechnical boreholes data sets that are publicly available. So we have also included that in the data set. So now let's say we are doing a pipeline in the Grand Prairie. So the pTerrain map, or the first terrain mapping, that will actually take the first 3 data sources that we're taking, and it's giving your information. Now, when the geotechnical engineer is reviewing that data, he has an extra second level of safety if he has any other available publicly available geotechnical report or soil borehole data close by. So he can actually make a more educated guess or more educated assumption on your soil based on that information as well. So we have 4 steps for gathering the data for this pTerrain.
Awesome. Thanks. Shama, another follow-up question here. You mentioned Alberta. How about other provinces like Saskatchewan or BC?
Yeah, sure. I mean, like right now we have done Alberta. We have data sets for Saskatchewan and British Columbia as well. So what we're trying to add more now, the other provinces are our primary target to start with the prairie region. So Alberta, British Columbia, and Saskatchewan, we have all these 3 informations. Now we are including Ontario and other provinces data. So we are currently working on that. And we are also including a lot of data sets from US, from the North Dakota side, South Dakota sides, all those information. So different states in the province, US, we are also including that one. And we do have the Saskatchewan and British Columbia data set as well.
So they are included as part of pTerrain, just to
Yes.
clarify. Okay.
Yeah, Saskatchewan and BC dataset are included in the pTerrain. We are also adding other provinces as well.
Good. Okay, I received a couple of questions via email. One of them is that how much time it takes to do the terrain mapping of a smaller pipeline, say up to 2 kilometers.
Yeah, I mean that's one of the solution that unique solution that we are actually providing, and that's why we actually made this software tool. So for smaller pipelines, we should be able to do it by within 1 day. So your pTerrain can actually generate your whole pTerrain map within 1 day. And what we need is the second version is that when we get the information from the train mapping, we need our in-house geotechnical specialist to review that soil data set from the train mapping to give a more educated assumptions on your engineering soil properties. So in other ways, like for a very small pipeline, it can be done within 1 day, and depending on like slightly larger or slightly mid-sized pipeline, we can finish it within 2-3 days.
Okay. I just received another question here in the window. How do you run the P-Terrain if you have many different soil properties? Do you use worst case scenarios to run P-Terrain for all pipe segments? Or do you divide the pipe segments according to the soil property and run each segment separately?
Yeah, no, this is a great question, but I mean, we don't assume anything. So all you just need is that pipeline coordinates and your right of way, right? So if you have the pipeline coordinates, whether it's a GIS file or you have simple northern eastern elevation coordinates, we just need to give this input to your P-Terrain map, and it gives you all the soil information that your pipeline is crossing. So even if you have 2, 3, 4 pipelines, we have separate polygons for different soils. So even if your pipeline crosses 100 polygons, it will give you 100 polygons or 100 information of the soil. So we are not assuming anything when you're running your pipeline data using the P-Terrain. In other way, or in a simplistic way, so if you have your coordinates of the pipeline, you run it through your P-Terrain, whatever soil your pipeline is crossing, we can actually give you all those information.
Good. Interesting question here. Can P-Terrain be used for existing pipelines, or it is for new pipeline designs only?
Yeah, I mean, that's a great question I actually covered in the last slide, is that like we can use it for both pipelines. Again, it doesn't really matter whether it's a new pipeline or your existing pipeline. So for the new pipeline or the existing pipeline, we just need the pipeline coordinates or a GIS file, whatever you have handy. So we can run those to our P-Terrain and can actually give you the information. So only difference between your new and existing pipeline would be your engineering properties of the soil. So when you're using existing pipeline, depending on when the pipeline was built, for example, if it was built for 20 years ago, then probably your soil is more like a drained fashion. So in that case, our geotechnical specialist will probably provide you more educated information on your existing pipeline. For example, like more like a drained fashion of your soils. So that's the only difference you're getting from the new and existing pipeline. But in the P-Terrain, it's actually applicable for both, whether it's a new or existing pipeline.
Okay. Yeah, that's what I have for now for the questions. Let's wait if you. I hope Shama answered your questions. For gentlemen who have asked the questions so far. We are here if you have further more questions. We're happy to answer.
Yeah, probably explained it so well that there's not many questions, but like, thank you guys. Like, these are really good questions. I mean, thank you for all the questions.
No, thank you very much, everyone, and really appreciate your time and interest in what we are presenting here today. Please check out our website. We are trying to make this information available and other updated projects available on the website. You are welcome to reach out to us anytime on any further follow-up questions. We're happy to answer and address those questions. Thank you very much, Shama. Thank you very much, everyone, for participating. I think we'll give you your 10 minutes, back to you. You can have the time. So thank you very much, everyone.